All right, here in this video in section 13.6, I want to talk about why the vector u has to be a unit vector in our computation of the directional derivative of f at a point a, b in the direction of u. All right, so recall this figure from our intro video. So imagine you're standing on this surface here, and you're going to walk along the surface in the direction of this vector u. Okay, and so looking at this cross-sectional view, we're really just asking, right, what's the slope of this tangent line here in orange at the point directly above the point P here, right? So what we did was we said, well, I'm going to go ahead and just take a little incremental step forward along my line L and choose a neighbor point on my green curve here, this cross-sectional curve, and then just find the slope of that secant line, and then I'm just going to take the limit of that secant slope, and that'll give me the orange slope. So in other words, we computed this difference quotient. Okay, so what does this have to do with u having to be a unit vector? Well, it has to do with the step vector right here. So first off, notice that if we look at this step vector, hu, and I ask, well, what's the magnitude of this thing? Well, by property of magnitudes, this scalar h here can come out front. And so this is h times the magnitude of this vector u. And see, if u is a unit vector, then this magnitude is just 1. And so this will equal simply this scalar here, h itself, if this magnitude is 1. Okay, and that's really what we want, right? Because when we set up this difference quotient, h here, the step size, is playing the role of the run, right? The horizontal change along our line L. And see, the problem if u is not a unit vector is that the vector here, hu, in blue, would not have a step size of length h anymore. Like let's say, for example, u has length 2. Then hu, by this calculation, would have a length of 2h. So in this difference quotient, I would have to put a 2h down here, right? And that's going to alter the value here of this difference quotient. Okay, the last thing I'll say here is that this same issue is going to come up with that alternative way we computed the directional derivative. This is where we parameterized our line L, and the u1 and u2, remember, are just the components of our direction vector u. And then this led to us using the chain rule. We said, well, z, our altitude, will depend on the coordinates x and y, but since we're restricting ourselves to this line L, these then will depend on this parameter t. And so then we looked at the derivative of our altitude z with respect to t, and this led us to this result that said that the directional derivative of f at the point AB in the direction of u was the gradient of our function evaluated at the point dotted with this vector u. Okay, but again, if u were not a unit vector, what would happen is that coming back just to the parameterization of the line, okay, if I increase this parameter t by h units, I'm not going to be moving forward h units along the line L. So if, say, the vector u had length 2, increasing t by h units would actually push me 2 h units along the line L, and that is in turn going to throw off all the derivative computations that we saw play out through this application of the chain rule. So we'd still run into problems even with this alternative approach, okay? So the bottom line is, right, if the vector that's given to you, that's indicating the direction you're moving in, is a unit vector, okay, then we're just going to fall back to this result here. In problem 2, we saw some examples where that direction was not given as a unit vector. So what do you do there? Well, you just normalize, in other words, divide the given vector by its magnitude to get a unit vector with that same direction, and then you use this. All right, that's going to do it.